Hi, welcome to EngPhys 3004 Lecture 2. We're going to talk about viscosity and surface tension today. So, viscosity. Let's talk about stress first. Shear stress is shear force per unit area. So, here's a picture that you had in 2P04. It's from this website. I didn't make this. And the shear stress is the shear force per unit area. We've got some pictures up here. So tau zx, remember these were the symbols. This means the shear stress on the z face in the x direction. Shear force was the force parallel to that face as opposed to perpendicular, which would be kind of like the force associated with pressure. So shear stress is similar to pressure in that it's force per unit area, except now it's kind of a sliding force rather than a pulling or pushing force on the surface. In a solid, shear stress is related to shear strain through an elasticity constant. Specifically, it was the shear modulus, capital G here. And we previously used gamma for the shear strain, but in fluid mechanics, that's already specific gravity. So, or rather, specific weight. Yeah, in fluids, it's already specific weight. So we're going to use beta instead for the shear strain. Okay, so shear stress is equal to shear modulus times shear strain. That's what it is for a solid. For a liquid, that's not true anymore. It's if you apply a specific shear stress, it's not going to move to a certain strain and then stay there. No, it's going to keep straining forever. That's part of what makes it a liquid. And so we have this thing instead. Shear stress is related to the rate of shear strain through a constant that represents the shear resistance or friction of the fluid, which is the viscosity. So here's shear stress related to the rate of shear strain by the constant viscosity. It turns out that the rate of shear strain itself is equal to the velocity gradient into the fluid. So as you move away from whatever wall we're talking about or whatever place we're finding the shear stress on, then the increase in velocity in, let's say, the x direction, if the wall is, we're going away from the wall in the y direction, would be the velocity gradient, and that happens to be equal to the rate of shear strain. So if we use this instead of our d beta by dt, then we can redefine the shear stress as mu du by dy. Okay, so let's explain why it is that the rate of shear strain is equal to the velocity gradient. Let's use this picture from the textbook to do that. We've got one plate up here, that's the thing in beige, and that's sliding past another plate, and there's this fluid in between. The fluid is thickness L, or the distance between the plates is L. Then we've got U plotted here. U is the velocity in the x direction as a function of y position. So U at 0, U at the bottom plate, is 0 because the bottom plate's not moving. U at the top plate is capital V, the velocity of the top plate. And we'll say that the velocity is going to be linear between the plates because why wouldn't it be? If the top plate is moving along at a constant velocity, the bottom plate is holding still. There's no other kind of flow forcing going on. Then we're going to have a linear velocity profile between the plates. And that means that U at Y is V over L, or rather Y over L times V, or in other words, V over L times Y. So that's just a linear function that starts at 0 and ends up at V once Y is equal to L. Okay, so that is the velocity gradient. Now let's calculate what the rate of shear strain would be. If the top plate is moving at velocity V, then in time delta t, the top plate moves a distance V del t, it should be a V. Yeah, and the shear strain developed was del beta, and for a small angle, assuming that we take this to derivatives, we can use the small angle approximation that says that del beta is approximately the tangent of itself, assuming that we have it in radians anyway. Then tangent being equal to opposite over adjacent is del A over L. And from what we had del A as earlier, substituting that in, we have that del beta is V del T over L. So then del beta by del T is V over L, which, if you compare to the velocity profile, is also du over dy. So to recap, we just proved that the rate of shear strain in a fluid is equal to its velocity gradient, where the velocity is measured in the direction that we're measuring that we're talking about the shearing in. So if we have y as the distance away from some wall, and we're looking at the rate that the fluid is shearing in that direction. So like this is a line that's originally vertical, and then the rate that it's opening up, the rate that the fluid is moving away at the wall, this is equal to the velocity gradient. In other words, the change in the x velocity as you move in the y direction. We needed this because we wanted to write this really nice definition for shear stress. Shear stress is what we call the viscosity, this constant, times the velocity gradient. And this is the result after the proof, when our original definition was that shear stress was the viscosity times the rate of shear strain. Now this is a good definition because it compares well with what we had as shear stress before. But it turns out that this is not exactly the definition of viscosity. In fact, viscosity needs a rearrangement of this equation. Viscosity is really defined as the derivative of shear stress by the rate of shear strain. So in other words, d tau by d, du by dy. Now, as long as the fluid itself is a Newtonian fluid, then the shear stress is linearly related to the rate of shear strain, and the viscosity works out and is a constant. This is an example of for water, a lot of oils, air, that there's a different slope for these different things, but they are all Newtonian fluids. An example of some non-Newtonian fluids would be things that have a shear stress versus rate of shear strain curve like the following. So Newtonian is the nice linear one that crosses through the origin. If it's an offset linear, like a Bingham plastic up here, then that means that you need to apply a certain shear stress before you get any rate of shear deformation. It behaves like a solid until you reach some threshold stress, and then it behaves like a fluid. An example of that is toothpaste or margarine. And we also have examples of pseudoplastics and dilatants. Before we talk about that, let's just pause and think, where is the viscosity in this diagram? Well, it's the slope. So the viscosity up here was the slope, and if we're looking at a diagram of shear stress versus rate of shear strain, velocity is the derivative of the thing plotted on the vertical axis with respect to the thing plotted on the horizontal axis, so it's just the slope in these diagrams. Now, strictly speaking, what we're talking about here is really called the apparent viscosity. If we're looking at these non-Newtonian fluids, viscosity is only defined for Newtonian fluids if you want to be really pedantic about it. So anyway, viscosity is the slope of these diagrams. So Bingham plastics are not fluids until they reach a certain threshold shear stress, and then they behave like a fluid with a constant viscosity that has to have some kind of threshold stress subtracted from it. Newtonian fluids, constant slope, no matter what shear stress or rate of shear deformation you're applying. Then we've got pseudoplastics and dilatants. Pseudoplastics start off like a very high viscosity fluid, but once you apply enough stress, kind of like a thresholding effect as well, they decrease their apparent viscosity. So they start off like they have a lot of viscosity, and it decreases as you apply more stress. Dilatants start off with relatively low viscosity, but if you apply too much stress, then they behave like something with a higher viscosity. So up here, we've got the oils with high viscosity, water, low viscosity, air, even lower. Pseudoplastics start off behaving maybe kind of like oil and then get more like water as you apply enough stress. Dilatants start off behaving like air, really resistant, really non-resistant to shearing stresses. In other words, small shear stress gives you a lot of shear strain rate, and as you apply more shear stress, they respond more strongly. What are some examples of those? Well, some shear thinning fluids, which are the ones that move very easily if you force them a lot, and don't move as much if you're gentler with them, are difficult to move slowly but relatively easy to move quickly, like wall paint and blood. Actually, you want blood to be like that because it needs to be able to move quickly through arteries, but kind of slow down if it needs to clot, like you've got a cut. So shear thickening fluids, dilatants, on the other side of it, would be silly putty, cornstarch water mixture, or the liquid bulletproof vest. I'll leave it to you to check out this video. This is some people running across a cornstarch water mixture. The fluid behaves like a really high viscosity fluid. As long as you give it enough shear, it doesn't move very much. But if you give it a little bit of shear, then it will allow motion more easily. Okay, viscosity, also called dynamic viscosity, sometimes the absolute viscosity, mu, is only one of two kinds of viscosity. The other one, kinematic viscosity, is the ratio of mu to the density. So it's just mu divided by density. Sometimes viscosity is listed in units of poise, although in SI it has units of Pascal seconds. Now a poise is 0.1 Pascal second. So 1 poise is a tenth of a Pascal second. Water at 20 degrees C has a viscosity of 1 centipoise, which is 1 millipascal second. Okay, question. What's the force on the top plate in the derivation we used to show that the rate of shear strain was equal to the velocity gradient? And what about the bottom plate? Well, the force is the stress times the area, and substituting in our relationship for stress, it's viscosity times the velocity gradient, for instance, or the velocity at the top plate divided by L. This is going to be a force of the fluid on the plate in the left direction on the top plate, and on the bottom plate it's going to be in the right direction. All right, let's get to some viscosity relations. Gases have viscosities that are governed by the Sutherland correlation. So mu equals A root T divided by 1 plus B over T. T is the temperature here. A and B are experimentally determined constants. This is a correction to the prediction of the kinetic theory of gases that mu is proportional to just the square root of T. So the term in the denominator, this plus B over T term, is the correction. It's independent of pressure from about 0.01 atmospheres to 3 atmospheres. This is probably something you are not too interested in right now, but I'll tell you, when you're trying to do some experiments and you really need to know what the viscosity is, this is going to be a useful thing for you to be aware of. Liquids have viscosity that's governed by mu equals A, 10 to the B over T minus C, where A, B, and C are experimentally determined constants. Liquids are generally much more viscous than gases. So here we come to an example of a plot of values. So these are experimentally determined for a number of different types of fluids, and you can see some general things. You can see that oils are up here at the top, more viscous than things like maybe different kinds of oils. Water down here, ethyl alcohol, mercury is across the center, then benzene, gasoline, and down here at the bottom are the gases. So gases being less viscous than liquids, with oils being some of the most viscous liquids. Water fairly inviscid among liquids, but not the least viscous. Okay, now another thing to note is that this is a plot of the absolute or dynamic viscosity, not the kinematic viscosity, where kinematic viscosity is dynamic viscosity divided by density. All right, now what do you think the kinematic viscosity would look like compared to the dynamic viscosity? So keeping in mind that the kinematic viscosity is dynamic viscosity divided by the density, then as density of gases is a lot lower than the density of liquids. So let's say water compared to gas, some of these gases, maybe air, water might be around 1,000 times denser, then you could have 3 orders of magnitude of this moving up. So depending on whether you're talking about dynamic viscosity or kinematic viscosity, water might be more or less viscous than air. Another thing is to consider the way that this changes with temperature. So liquids are not changing their density too much with temperature in this kind of a temperature range. Gases can change their density a fair bit. So gases on this temperature range are going to be having a lot lower density on this end than they are over on this end. How is that going to change the plot of kinematic viscosity? Well, in addition to the gases moving up because of their lower densities, it's also going to slope these curves, but it's not going to slope them the same way that the liquids are sloped. They're actually going to be dividing by smaller densities at this end than at this end. So we're going to have higher slopes on the right than on the left, or rather a higher value on the right than on the left for the gases. It's going to be sloping more positively in this versus this temperature axis. So there really is different physics governing how gases are working versus liquids when it comes to viscosity, and the approximate relations here are based on some predictions from kinetic theories of gases, but the fact that we have to correct it to match reality tells you that the real physics underlying this stuff is quite complicated. This is going to be a theme in this fluid mechanics course, that the physics underlying how fluids work are generally quite complicated, so we're going to be relying a lot on tables of experimentally determined values in order for us to do some engineering with it and make real predictions. This isn't to say that there's nothing that we can say about it or that you should just give up. On the contrary, because other people have done all the work to get those tables, we can get some pretty interesting results quite quickly if we're just willing to use them. All right, well, how do they come up with this set of data? How do they come up with this plot in the first place? You need something that can measure what the viscosity is as a function of temperature. How can we get the viscosity? We could, if we could somehow take, for a given fluid, plot the shear stress versus rate of shear deformation, then we could get the viscosity. However, calculating shear stress and rate of shear deformation directly can be kind of tricky. So we're going to make another calculation, which is plotting two things that are proportional to these, and that is with something called a viscometer here. We are going to measure the torque that's applied to this shaft and its angular rate of rotation and show how that's related to viscosity too. If you wanted to, you could recast each of those variables back in terms of shear stress and rate of shear strain as well to make the plot with the same axes as this. But if we can come up with something that's proportional to viscosity anyway, and that's all we want, then we don't need to do that. So here's how the viscometer works. You put a little bit of fluid in between this rotating center cylinder and a stationary outer cylinder, and then you apply a given torque to the inner cylinder and measure how fast it moves. Or equivalently, you make it move a certain speed and measure how much torque was needed to do that. Here's how the viscosity comes out of that. The shear stress on the inner surface here, so the surface of this inner cylinder, is viscosity times the velocity gradient, rate of change of velocity in the around direction with respect to position in the radial direction. And this velocity gradient is equal to just the change in velocity divided by L, assuming L is small. Then whatever the velocity profile is, this small thickness, the linear profile should be reasonable. And we can write out what that difference in velocity is by saying the outer one's not moving, so it's just the inner velocity, r omega. Okay, so that's the shear stress. The torque is the force on this inner cylinder, which is the shear stress times its area, force multiplied by the radius of the inner cylinder. The area of that inner cylinder would be circumference 2 pi r multiplied by the length coming out of the page, however long this cylinder is. And so we get that the torque is equal to mu r omega over L, the stress, multiplied by 2 pi rl, the area, multiplied by its radius. Calculating this all out, we have something with all physical things that we would know, an angular velocity we can measure, and a torque that we can measure to calculate what the viscosity is. You have to do this at a bunch of different temperatures because viscosity in this plot is a pretty strong function of temperature, as you can see. So when you're doing this, you're going to also want to be able you're going to also want some way to measure the temperature simultaneously. All right, our second topic for today is surface tension and the capillary effect. Surface tension is the force per unit length of surface and also the surface energy per unit area of surface. So force per unit length of surface and the surface energy per unit area of surface. You think, okay, how can that be the case? Well, we'll see. These arise because molecules in a liquid are more strongly attracted to each other than to the surrounding air, and consequently, the interface requires energy to maintain. So that should make sense. As the molecules want to be closer together than they want to be with molecules of the air, then this is like an unhappy molecule compared to this one. So they would want to move this, which means the surface itself takes energy to maintain. This is responsible for water forming beads on leaves, insects being able to walk on water, and the capillary effect that we're going to have a section on right after this. Surface tension has units of force per length, as we said. So you multiply by the length of the interface edge to obtain the force on that edge. Let's see what we mean by this. So here's this maybe soap bubble or something on this wire, and then as we try to move this wire, we have to fight the surface tension. In fact, we have to fight the surface tension just to hold the wire in place. The surface tension is going to want to make this collapse. All right, here's the top view of that same wire. We've got some surface tension on this side, surface tension on this side, and it's fighting a force. So the force on each of these edges is the sigma s multiplied by the length of the edge, and that's what we defined up here if surface tension is force per unit length. Let's see how it can also be the energy per unit area. So each side of this soap bubble is taking some energy to maintain. It's got a potential energy, because if we were to let go of the wire, it would collapse and release that energy of sigma s multiplied by the area. So the surface tension multiplied by the area. Now the area is B multiplied by X. And you remember that potential energies have a force associated with them given by negative the gradient of the potential energy, which means the force associated with this particular potential energy would be negative its own gradient. So we could say like force of the surface tension is equal to negative grad of U, which is negative, this is only a one-dimensional, it can only move in x, negative d by dx of sigma s, and then the area, bx, which is equal to negative sigma s times b. Aha, so look at that. The force of surface tension is equal to negative sigma x times b. The negative means that it is in the opposite direction of the direction of increasing area, which was positive x. So the surface is providing a tension force. Each side of the surface gives a force of sigma s times the length of that interface. And that's how the definitions are the same. That's why this sigma s is simultaneously the energy per unit area of surface and the force per unit interface length. Now in the picture, we put F as the force that you'd have to apply to the wire, so that's just negative this, and since there's one surface on each side, we have double that force, and that's how you get 2 surface tension times B. Note that the surface tension, this sigma, is not actually a tension force. It's only a force after you multiply it by interface length. Let's look at some values for surface tension. Surface tension of water changes a fair bit with the temperature. Low temperature water has a really high surface tension. It's like, come back, other water, I want to be close to you. And high temperature water is like, I got no time for that, I'm getting out of here. It has a low surface tension. It wants to just move wherever it's going to be. And then we've got other materials in here which have different surface tensions. Let's look at some of them. So what's the highest one on the chart? It's mercury. The lowest one on the chart is this high temperature water. But the other one, who knows what these other things do at high temperature. That's interesting. A side note is that water has actually a pretty high surface tension around room temperature. So it's the second highest thing on this chart. It's around, it's more than twice most of these other things, except for mercury. Why do you think mercury has the highest surface tension of any of these? I'll leave that to you to think about. Keep in mind that mercury is still a metal, even though it's a liquid. So it can do kind of like an extreme version of the hydrogen bonding that makes water want to be so sticky and happy in the liquid form. Now, moving on, let's look at one calculation example that we can do with surface tension, which is kind of interesting. Bubbles suspended in a liquid are pulled in by surface tension, but they don't collapse because they're held out by having a higher pressure on the inside. So a bubble imagine like a bubble of air underwater, then the there's an unhappy water surface there, so it wants to collapse. You could think there's like an air surface as well. You can calculate how much pressure difference there is by equating the pressure force and the surface tension for a cross-section through the center of the bubble. Here's a picture of that. We've got water, say, on the outside, and that wants to collapse this unhappy surface, but as it does, it shrinks this pocket of air inside, which raises the pressure of the pocket of air, and that says that it can't collapse. So the pressure is too high, it's stopping the collapsing from happening. If you balance those forces, then you can say, well, the pressure force, the total force on this face, must be pi r squared, the area, times the increased pressure inside the droplet, the pressure that's higher inside versus outside, and the surface tension, 2 pi r sigma s. So we come up with the increased pressure inside is 2 sigma s over r. Bubbles are gas droplets in liquids. The same surface tension calculations work for liquid droplets suspended in a gas. Now, you may find it easier to understand the soap bubble version of this, and that's this example here. So we've got air on the outside, we've got air on the inside, and we've got this thin membrane of liquid, which is a soap bubble. Now it works basically the same math as we just had, except there's two surfaces that we're crossing here as we go from the inside of the bubble to the outside. So we still have the same pressure calculation, the change in pressure inside versus outside the bubble. And we've got two surfaces now, 2 times circumference, 2 pi r, times the surface tension. So this has to balance this pressure, and you find that the increased pressure inside a soap bubble is just double the surface tension calculation we had last time, so 4 sigma s over r. You can also derive this relationship using the energy interpretation of sigma s. Let's give that a shot. Consider adding some more liquid to a liquid droplet. It expands so that the surface energy must have increased. If we look at the rate of change of the surface energy with respect to the increased mass, then that's sigma s times the area, and that is factoring out sigma s because that's holding the same. We can substitute in the area, 4 pi r squared, for area of a sphere, and looking at the rate of change of this with respect to mass, we take out the 4 pi, that's not changing either, and then take the derivative of r with respect to m. We just have dr by dm. And the expansion must have done work. The work that happened is force times the change in the radius, and the force it was working against depends on the pressure. Therefore, the change in the energy of the surface has to equal the work that happened, and equating those two, you come up with the same pressure relationship that we just had. All right, takeaway is that a bubble exists because of a balance of surface tension and higher pressure inside. Pressure increase inside versus outside is preventing the bubble from collapsing, and the reason it wants to collapse in the first place is because of surface tension. Balancing these out depends on whether you've got a soap bubble, which has double the surfaces, or an air bubble in liquid, or a liquid bubble in air. The liquid bubble in air or air bubble in liquid is 2 sigma s over r is equal to the increased pressure, whereas the soap bubble, the increased pressure is just double that. All right, question. Why can an insect walk on water, but you can't? Aren't you both subject to the same surface tension? Well, it's mainly because they're smaller. The reason for this is force scaling. Surface tension is proportional to length, while gravity is proportional to mass, which is proportional to length cubed. So other things equal, if you make so how tall is an insect? Maybe a couple of millimeters. And how tall are you? Maybe a couple of meters. So you might be 1,000 times larger than an insect, which means that when you're on the water, the surface tension force for you is around 1,000 times bigger. That's great, but gravity on you would be 1,000 times big, or like 1 billion times bigger. Okay, so the relative size of gravity versus surface tension for you versus a couple meter high insect is 1,000,000 times stronger. So you experience gravity at relatively 1,000,000 times more powerful than surface tension compared to what that insect would feel. The last application of this that we're going to do is, as promised, the capillary effect. Capillary effect is the rise or fall of a liquid inside a small diameter tube, a capillary or a capillary. Now, you probably have been told that you need to read to the bottom of the meniscus when you're reading from a graduated cylinder, and this is the reason. The fluid is going to lip up close to the wall because of surface tension. And in addition to that, it is also going to rise up so that the liquid level sits higher if you were to put a straw into a pool of liquid and the liquid wants to stick to the straw compared to if it doesn't. And this kind of depends on what's called a contact angle between the liquid surface and the straw surface. So there's really three different things involved, three different materials involved when we're looking at capillary effect and contact angle. It's an interaction between the liquid, the solid, and the gas that's around. So you probably would have pictured that it would look something like this if you just look at the surface tension picture that we had previously, where the molecules of the liquid want to be close to the molecules of the liquid in preference to everything else. And that's the picture in mercury. So you would imagine that when you put a straw into a liquid, it would say, no, I don't want to be in that straw because then I need this extra surface where I'm not connected to more liquid. I don't want that. But mercury, remember, has a very high surface tension. It turns out that you can, for water, have a situation that you're probably more familiar with, where it actually rises into the solid if we've got like a glass tube sticking into the water. And that's because the water is actually more attracted to the glass than it is to itself. So the water wets the surface of the glass. The mercury does not. This is the phrase that we use. If we have a contact angle less than 90 degrees, meaning that it wets the surface and rises in the capillary, then the water must have been more attracted to that surface than it was to itself. On the other hand, if the contact angle is greater than 90 degrees, then it falls in the capillary, does not wet the surface, and the molecules are less attracted to the glass than they are to themselves. The amount that the liquid rises or falls in a capillary is the point where the surface tension, which is going to be 2 pi r surface tension cos theta, is equal to the weight displaced by rho g pi r squared h. Now here's an unfortunate situation you're going to encounter. Surface tension is both the name of this force per unit length constant, sigma s, and sometimes we'll say, like I did here, surface tension when we really mean surface tension force. So just keep that in mind and watch out for context whenever you're using this. Now, why is this the case? Why does this have to balance? So here's a picture. The contact angle that it's making, which is sort of the angle of the water inside, you can see an acute angle, we said, means it's wetting the surface, so that means it's more attracted. That's the kind of a similar triangle type thing, or just kind of equivalent angles of this one to the one inside. That's the contact angle measured there. So for an acute contact angle, it's wetting the surface, it's rising up. The force in the upward direction would be the cos of this multiplied by the circumference, 2 pi r, times sigma s. So that's just the length, 2 pi r, times sigma s. That's the force. The force is not in the up direction, though, entirely, so we need to take that cosine. And this is displacing an amount of water up the tube, which is roughly kind of ignoring the effect of curvature here, which is, despite the picture, in most situations the capillary rise is pretty extreme. So you can ignore the difference in the edges here and just say that the weight is the height times the area of a circle, pi r squared, times rho g. Okay, so set that weight equal to the surface tension force, and we have a formula that calculates the capillary rise. Interestingly, This works whether the surface tension was making the water rise in the capillary or fall in it. So whether the contact angle was acute or obtuse. So how does that work? Well, cosine is going to give you a negative sign if theta, or phi rather, is greater than 90 degrees. And that means that we've got the situation of mercury where the capillary rise is actually negative. Final question for today. To see the most capillary rise, should you use a small straw or a large straw? Well, we want the radius to be as small as possible. So assuming small or large is talking about the width of the straw, we should use a small straw to see the biggest height.